Okay, I'm running. Okay, we are back to learning prop logic, and last time we did rules of equivalence slash replacement, and I told you sort of like the structure. So there's gonna be like this kind of like a, um, like a kind of form one and form two, which is going to be joined by this metalinguistic sort of equivalence, logical equivalence operator, which basically tells you the replacements. So we went over De Morgan's law, we went over association, we went over distribution, we went over commutativity, double negation, and now we have five more left. I asked you some questions last time, which we are still yet to solve. We'll get there, um, but I'll first finish the remaining um, five rules of replacement, and then we can go to the other one.
Just to double check the question you asked me to solve, could you show it for a second?
Yeah, one sec.
So, I wanted to ask, is this supposed to be the disjunctive syllogism?
Yeah, this is the disjunctive syllogism.
So should the conclusion be not Q or Q?
Sorry, it should be Q.
Okay. So I changed it to Q, and
Yeah.
I think I managed to solve it using material implication.
Okay. Okay. We'll see it.
But with not Q, I couldn't solve it. I
Yeah, yeah.
was
It shouldn't be not Q. It should be Q.
cool.
Yeah. Okay. So let's start um, with the sixth um, you know um, rule of equivalence, and this one is called contraposition. Okay. Contraposition, I'll just tell you the rule. Basically, it's going to be alpha implies beta is the same as not beta implies not alpha. Okay.
Hmm.
So this, you're just gonna get this by modus tollens, right? So if alpha implies beta, then if not beta is true, then not alpha is true. That's how you get this.
Yeah, I'm following.
Okay. We'll try to prove all of this later as like an exercise. But at this point, I can give you like a semantic, you know, explanation using truth tables. But yeah, anyway, the next one is the seventh one, which we can do material implication.
So we briefly saw this one last time.
Exactly. Yes, we did.
So I think I can say this one out.
Yeah,
You
sure.
can correct me if I'm wrong. So it's P imply well, alpha implies Q or alpha
Beta.
implies beta. Yeah.
Okay.
And then that's the same as not alpha or beta.
Exactly. That's the one. Yeah, so you already understand this. And the way we get this is just the truth conditions for a material implication is just false antecedent or true consequent, and an inclusive disjunction of that. That's just how we get this, like a semantic equivalence. Wait, did I start the recording? Yeah, I did. Then we have the next one, which is material equivalence. There are two of these, okay? So this is alpha, double implies beta, or alpha if and only if beta. That means alpha implies beta and beta implies alpha. I've got to separate them out with brackets. That's the first one, okay? So that's 8.1. Then we have 8.2, which is alpha double implies or if and only if beta, same as the upper one, is logically equivalent to alpha and beta, or not alpha and not beta. Does this second one make sense to you?
I guess if we did the truth tables, it would work out.
Yes, but without looking at the truth tables, when is a biconditional true?
So when they both have the same truth values.
Yes, and when
Both
does
variables.
that happen?
So that happens when uh when they're both true, or yeah.
Yes, when they are both true or they are both false.
Okay.
So alpha and beta means alpha is true and beta is true, right?
Yeah.
And this means not alpha is true, which means alpha is false and beta is false. So when both are true and when both are false. So that's just how we get this. And yeah, when we do the truth table, obviously it'll come out like that. So that's the 8th one, okay? I hope this makes sense. Then we can go to the 9th one.
Good.
Yeah, what to say?
Eight,
Something?
yeah, 8.1, it would be possible to write it as switch the brackets around as well, right? So
Oh
could we
yeah.
write
Why? Can you tell me why? Like, what rule would that be?
that would be well, we learned it last time. Would it be commutativity?
Commutativity. Yes.
Yeah.
Yes, that'll be commutative. So, conjunctions and disjunctions are commutative. So you can flip either of them around and it'll be the same way.
Cool.
Yeah, you're getting it. Then the next one is exportation. Sorry, one sec. Exportation. This is a bit interesting. So exportation takes the form alpha implies beta implies gamma is logically equivalent to alpha and beta implies gamma. Okay?
Okay.
So can you give me like a Okay, we'll do it. And the 10th one is a bit is called tautology. We've already discussed tautologies. So there are two types of tautologies. One is what?
So tautology is when all the rows are true, right?
Yes.
The was it E or not P?
P or not P, that's one kind of tautology. But in this case, we are talking about a different. Um, we are talking about tautology in like in the English sense. So our tautology here is alpha is the same as alpha and alpha, and the other is alpha is the same as alpha or sorry or alpha. So this is again tautology. So yeah, those are the 10 rules of inference. Sorry, rules of equivalence. We've already done 8 rules of inference and 10 rules of equivalence. So I guess we can go back to trying this one. Yeah.
So this one I tried to do it using material implication,
Okay.
and it was a little bit different because yeah, I wasn't sure if I could do the negation of it, but what I did was for the third premise I wrote not P implies Q.
Implies Q.
And then I did that.
Can you show me how you got that? Like, yeah, this is correct. But like, how did you get this?
So I just did it by visual inspection, really. So uh, the normal one is P implies Q,
Yeah.
and then not P or Q is this the equivalent version.
Yeah. So I'll allow that, but I'll also show you the, like a more precise, a more elaborate way of doing it. Like you don't need to do it, like you can simply look at it and tell me this is material implication and I'll be happy, but I want you to know, like this is how, like if I want to, if somebody asks you to explain how you got that, this is how you'll do it. So you got this right, you can do not P or Q, and this will be what?
Double negation.
Double negation, exactly. And then now what you can do is you can bracket off this one, and then you have false antecedent and true consequent. So the antecedent here is not P, and the consequent is just Q. Okay, and we are getting this from 3 material implication. And what's the 5th step?
Fifth step was Q, and we do
Okay.
modus ponens
Modus
on
ponens on
premise 2 and 4.
2 and 4 modus Exponents. Exactly. Yeah, that's how we do it.
Cool.
Okay. Yeah. So yeah. It took a it took some time, but we got there.
Yeah.
Um, so yeah. So let's uh, you know. So before we go do more problems, let me introduce to you the concept of um, different proof strategies.
It's
Um,
never ending.
yeah, it's never ending.
Yeah, I was reading the book, and then there's a point where the author says, "Ah, you're on 28 rules now," or something like this.
Oh yeah, like if you include the, you know, rules of syntax and all of that, I think it.
Then there's also by conditional rules.
Oh yeah, biconditional rules as well. Yeah, we have those to cover. But the thing is, if you, as long as you're not memorizing them, you can sort of derive them on the spot. Like once you're familiar with like the symbols and all of that, um, you're familiar with like the relationship between them. You can basically just um, derive each of them on the spot. You don't even have to remember the names. Like I wouldn't expect you to remember some of the names, but as long as you're telling me what rule of inference you're doing, like you don't have to tell me the name. You can just tell me, oh, this is like this rule of inference, like uh, uh, you know, like if you tell me that, like that'll be fine. But these names are not very hard to remember either. So yeah, it's nice to sometimes um, yeah, just remember them.
I don't know if I went to the someone from the public and I said something such as disjunctive syllogism, hypothetical syllogism,
Yeah,
I think they will be thinking, "What am I talking about?"
yeah, they'll also think that you're smart. Yeah.
Yeah. Yeah, it makes you seem smart.
Anyway, so we can talk about like proof strategies. So so we already know that you can prove something using like a semantic like a semantic technique. Like for example, you can have um, truth tables, and you can have truth trees. You can also do a syntactic proof, um, and that is the that rules using rules of inference, etc. Equivalence. Okay. Um, but how do these like work, right? So there are like two kinds of strategies that you can apply. One is called an indirect proof. This is more familiarly known as proof by contradiction. I'll just write P and not P because now we are logicians. We are no longer uh, uh, common people. So this is proof by contradiction. It's also called another thing. It's also called even more familiarly maybe. It's called reductio ad absurdum. And this is like sort of in the words of Daniel Dennett, this is like the granddaddy of all proofs in history. Literally, or like there's no, I don't think there's any domain of science or maths which does not involve the usage of an indirect proof. Every single one, like even if you are thinking of like physics, there's like reductio ad absurdums in physics. Um, there are reductio ad absurdums in geometry. Everywhere you'll find reductio ad absurdum being used a lot in direct proof, whatever it's called. Um, and the other one is conditional proof, which we'll discuss. Conditional proof. Conditional proof basically. So I'll briefly tell you what's the structure of each of them. So the structure is you start with some proposition, like you want to prove something. What you do is you assume that thing is false. So let's say I want to prove P. So what I'll do is I'll actually start with not P, and then using not P, I will see where that takes me, and maybe at some point it will lead me to Q and not Q, which is a contradiction. And we know, according to the law of non-contradiction, if this is according to the law of non-contradictions, all contradictions are false. So you started from somewhere and you reached a contradiction, which means you can modus tollens all the way back, and then you get not P, which is the same as P. So the idea is, if you start with some proposition and you end up with a contradiction, your initial assumption was false. So now you have basically proved that you've proved P by proving that not P is false. You got what I mean?
Okay.
Yeah.
Because
So
from the contradiction, you can go back to either P or to not P.
yes. So let me show that even more like clearly, so as to leave no scope for confusion. So let's say you start with the assumption of not P, okay, and you somehow reach a contradiction. Right? Now this is a conditional, right? Like this is a conditional statement. Not P implies contradiction. And we know contradictions are always false according to the law of non-contradiction. So when the consequent is false, in order for this thing to be true, what is the truth value of this?
Could you repeat the question?
Yeah. So this conditional is true, right? This conditional is true.
Yeah.
And the consequent is false. So in
Then
which
this one might be true, the not P.
Not P will be true?
If
Really?
no, false. Wait, let me remember what the conditional was.
When is a conditional false?
False. It'll be false.
Yeah. Because a conditional is true when both of them are true or false, or when both of them are true. But when the antecedent is true, the conditional is actually false. Like
When the consequent is false.
when the consequent is false and the antecedent is true.
Yeah, that's like the one condition where the conditional is false, right?
Exactly. But in this case, we have clearly shown like the conditional being true. We have started from here and we have reached here. So we have shown that the conditional is true, and we know the truth value of this. So we can infer the truth value of this by law of non-contradiction. Um, this is always false, and if this is always false and the conditional is true, this must be false.
Mm-hmm.
So we have shown that not P is false, which means P is true.
Yeah.
So you have proved that P is true by showing not P is false. It's the same thing, right? Like you show not P is false, you show P is true, both are the same thing. Like according to bivalent logic, regardless of what you do, you can show one is true and the other is false, or you can show the other is false and this one is true. It doesn't really matter. But you've basically shown that not P is false. So you've shown
Yeah.
that your initial assumption, which was the opposite of what you wanted to prove, is false. So your whatever you wanted to prove has been proved. So that's what an indirect proof is. And with some creativity, you can actually just use indirect proof for any kind of proof. Literally any proof, any argument can be shown to be valid if it is valid, of course, granting that any valid argument can be proved to be valid using an indirect proof. You can, yeah. One sec. Are you still there?
Yeah, I'm still there.
Okay, yeah. I heard some disconnect noise, but okay. Um, yeah. So you can use indirect proof to do any kind of proof. Any kind of argument I give you, you can do an indirect proof, and yeah, you can get by with it. And truth trees actually use indirect proof. So that's an interesting relationship, and we will when we get into truth trees, it will be apparent why this is true. Okay. Now, conditional proof is when you want to prove that some conditional is true. Let's say there is a conditional, okay? Let's say the conditional is P implies Q, and I want to show that this is true. Now, what I can do is maybe I have some other premises, but I'll start with assuming that this is true. Okay, I'll start with assuming that P is true. Like I'll write like this is an assumption, and then we can eventually get to Q. We can show that P implies Q is true, using other like in some other way. Like let's say I had another proposition like let me show you a proof anyway. Yeah. So let's say I have these premises and I want to prove the conclusion. I want to prove this. So this is my conclusion. This is my conclusion. Okay. What I can do is I can assume P, and I'll see if it follows. Okay. So from P to R, it's a modus ponens, and from R to Q is another modus ponens. So you started with P and you've arrived at Q, which means P implies Q is true. Right?
I didn't quite follow.
Okay, we'll do it again. One sec.
So you have the three premises, or okay, P implies Q is the conclusion.
Yeah. Now this is a very this is a very straightforward argument, which is why you might not see like the utility. Um, but yeah, like I'm just showing you the mechanics of conditional proof.
Could you show me again?
Yeah, yeah.
Uh, So just like yeah, one step at a time because I didn't catch what you're
Yeah,
doing.
yeah. So this is what you want to prove, right?
Yeah, P implies Q.
Yeah, and you have these two premises. Now what I
Yeah.
can do is I can assume P to be true. It's just an assumption.
Okay.
Um, you can
So
write
if,
assumption for conditional proof. Okay.
all right. So if P is true, then R will be
Exactly. So if P is true, then R follows, right? And this will be what?
what does the ACP stand for?
Assumed conditional proof.
Okay, then.
Assumption for conditional proof.
All right. So then R is also ACP.
No.
No.
Take a look.
So P is true, and then you want the whole premise to be true.
Mm-hmm.
So then, if you want both of them to be true for the premise to be true.
No, no, no. One sec. Hold on. So this, okay. So I have these two premises, right? The
Yeah.
this is premise one, this is premise two, and this is what I want to prove.
Mm-hmm.
Now, what I can do is I can assume P to be true.
Mm-hmm.
Okay, and I'll specify. I'll say this is an assumption for conditional proof.
Okay.
Now you can see that this is what?
This is modus ponens.
Okay, what do you get with a modus ponens?
So then R will be the next line.
Okay, and what is
So you modus ponens
on
on 2 and 3.
2 and 3, right?
Yeah.
Now what's the next step?
Next step is that can we just assume R as well?
We don't need to assume R. We have already, from this assumption, this already follows. We don't need to assume.
All right. So then we can do another modus ponens.
Okay.
So then we get Q,
Okay.
and then this time we're doing it on the first premise and premise 4.
Okay. Right?
Yeah.
And basically, we started with P and we have reached Q.
Got it.
Right? So if
So
P is true, then Q has to be true.
Yeah.
Which means
I see what
P
you did.
implies Q. And I'll just write CP from 1 to 5. 3 to 5. Or you can write 3, 4, 5.
Before I think we were writing the
Oh, sorry.
the line.
Yeah.
Well, no, I mean like in the last less times we were doing the operator first and then the line. Today we changed it for some reason.
The operator first.
I think before we were writing what we did, so modus ponens or modus
No.
ponens. Then
We were doing the this thing first. The premises first. Look.
All right, cool.
Yeah. Yeah. So that's we maintain that. Don't worry. Okay. So this is 3, 4, 5 conditional proof, and that's QED, right?
Mm-hmm.
So yeah, that's I just gave you an example of conditional proof. So might as well give you an example of
Indirect.
indirect proof, exactly. So do you remember constructive dilemma?
Yes, more or less.
What was the rule?
The constructed dilemma was alpha implies beta.
Okay, so in this case we'll use P. P implies Q.
E implies cube, and then it was R implies S, or
Mm-hmm.
and then P or R,
P or R.
and then for Q or S.
That's the conclusion, right?
Yeah.
Okay, let's prove this. And so the first step in proving this is negating Q or S. Okay, this you write assumption for indirect proof. Assumption for indirect proof. Okay, where do we go from here?
So now we're trying to get from this to the first premise. Is this what we're going to be doing?
No, we're gonna try to get a contradiction.
Okay. All right.
So
So what's the end result that we want? That we want a Q and not Q,
we
or
don't
something
know
like this?
that. We don't know that right now. It could be anything. It could be some contradiction. So yeah, like don't look at what you want to prove. Like just see where this takes you. So what would you do with this? Like you see a negation and you see a disjunction inside a bracket. What would you do?
Can we expand it out?
Yeah, how?
So what was it? We add a negative, and then we change it to a conjunction.
Yes, and that
Calling it-
was what rule of equivalence? There was a guy's name.
De Morgan's
De
law.
Morgan's law, exactly. So you get not Q and not S, right? And you can say this
Yeah.
is for De Morgan's. Okay. Now you got not Q, you got not S, right?
Mhm.
What other rule of equivalence can you apply here?
We could. Uh, 1 minute, I can't remember the names.
It doesn't matter. We can like tell me what you would do. Like what's the next step?
Well, you could just write one of them, like
Exactly.
not two.
So that's simplification. Okay. So I'll guess this, I'll get this, and I'll write um, 5 simplification, and then I'll write 5 simplification. Okay, now you've got not Q and you've got not S, right? And now you've got these premises with which have, like, implications. What will you do?
We can do modus tollens.
Modus tollens. So
So not P.
not P, and that's
And we did it on the first premise, and this premise 6.
okay. That's modus tollens, right?
Yeah.
The next one.
And then we can do it on the modus tollens again on premise 2.
Okay, what's that?
So not R.
Not R, exactly. And so that's 2 and 7, right?
Yeah.
2 comma 7. Modus tollens. Okay, now you have this, you have this. What can you do?
Addition.
Addition. Yeah, addition. Well, it's conjunction, not addition.
Conjunction. Okay.
Yeah,
I can't remember.
you'll get it as you keep doing proofs and you keep telling those names. You'll get it. Practice makes perfect.
Perfect. Yeah.
So you have not P and not R. Now look at what premise 3 is. Can you do something that will make this similar to this?
We can do a De Morgan's law.
Again, exactly. And what will you get?
So we take out the negative, and then P or R.
Exactly. Now
And then
look at this. Not P or R, P or R. So what can you do with those two?
go up again. So I can we can just do another addition with them.
Conjunction.
Conjunction, yeah.
Yeah. And voila, that's a contradiction. Oh, sorry, we have to write the rules here, right?
So there we did, De Morgan's law.
No, this is not De Morgan's
Oh,
law. This is conjunction, 8,
Junction,
9.
yeah.
Conjunction, gotta be careful with those. Should not rush.
And then
This is 10 De Morgan. This is
conjunction.
3, 11 conjunction. And that's a contradiction. Right? So we just conclude that Q or S is true. And you can write reductio ad absurdum.
Okay. So what we did was we took the opposite
of what we wanted to show.
And so we take the opposite of the conclusion,
Mm-hmm.
and then we show that when you use the opposite of the conclusion, you get a contradiction.
Yes.
So then the opposite of that conclusion is uh, it means that it's a valid argument.
Yes. So some people like to write RAA, some people like to write IP, indirect proof. Um, no one will beat you up over that choice. Like, it's up to you. Um, but yeah, so we just write QED after this. So notice when we started, right? I did not know. I honestly did not know what the contradiction would be, right? Like, you asked me, like, what is the contradiction that we are trying to arrive at? I actually didn't know. Um, but as we progressed, I saw something coming together. Like, we were just applying rules of replacement and then rules of inference, and when then we got something, and then we just made it look like the negation of whatever we want to, uh, you know, whatever was in the premise. So we got a contradiction. So in the beginning of the proof, I did not know this was the contradiction that we were going to get, but we got it simply by applying the rules, and then
Okay.
we got this, right? So that's an example of an indirect proof. Now, what you can do is you can go through the first 40 questions that you solved for using the first four rules of inference. At least some of them you can try doing it with um, a reductive ad absurdum, and then that'll really make it like make you very comfortable with it. Like, let's try one more, because this is going to be like this is a foundational concept, sort of, so to speak.
How
um,
do you decide which method to use?
that is a bit of like sometimes it's sort of like an easy, like sometimes you can just look at the problem and figure out like what, like, the first kind of proof that comes to your mind, that'll be like your like, like um, when I look at some argument that I want to check if it's valid, like, I can sort of eyeball it, and at this point I can eyeball it and tell you whether like it's valid, and I can sort of tell you what the proof is. So in that case, I don't need to do a reductive ad absurdum. Um, but if I wanted to very rigorously show that, then I can either either like give you like a um, you know um, like a truth, like a like a natural deduction, like just going through all the rules of inference and doing that. I can either do that, which is what I probably have done in my head, or I can just do the reductive ad absurdum and show it to you. But like, the thing is, if when in doubt, reductive ad absurdum.
And could you explain one more time exactly why that shows it's just so it's completely clear for me
Sure.
why,
Yeah.
like the diagram you drew out right at the start.
Yeah. So what do we want to show? We want to show P. Okay. We want to prove P. So what I'll do is I'll assume that P is false.
So
And
well, when you say so P is our conclusion, right?
yeah, P is the conclusion. Okay, P
Okay,
is the
so we
conclusion. So
yeah
I'll assume uh, not P to be true. I'll assume that P is false. Because what does not P mean? Not P means P is false.
yeah.
So I'll assume P is false, and then I'll apply some rules or whatever, and somehow I get to some kind of contradiction. Okay. Now, remember in conditional proof, when we start with something and end at something, those two things are, bound by a conditional, right? So in this case, you started with not P and then you ended at Q and not Q, right? So this is the conditional that you got.
Which one was when you say in conditional proof? So, yeah, I cannot remember exactly when we did that. So, if we have two premises, we can just write it as not P implies what comes down later on. Is that what you're saying?
Yeah, exactly. So you've started with this and you've ended at this, right? Which means
Yeah.
this implies this.
Okay. Yeah.
Yeah. Okay, so you start with this, you end at this, which means this implies this. Okay, so I've written that down over here. Now, by law of non-contradiction, we know that this is false. Because what does the law of non-contradiction say? The law of non-contradiction says that all contradictions are false.
Okay.
So wherever you see a contradiction, it will automatically get the truth value of f.
And this law of what's it called? The law of non-contradiction?
Law of non-contradiction, yes.
So this just means that. So I'm not sure if I cannot remember if we specifically said this law, but we just said that a contradiction has all of its truth values are false. So that's just the law.
Yes.
So it's the law of contradiction, the law of non-contradiction.
Law of non-contradiction. It's called non-contradiction because contradictions are false.
Sorry, you cut off for the last bit of that sentence. It's called.
Yeah, it's called law of non-contradiction because non-contradiction means what? Not contradictions, which means contradictions are always false.
Okay.
Okay, it's called law of non-contradiction. Okay, so
actually, I still don't get that. So the contradictions are always false.
Yes.
So why isn't it called law of contradiction?
So non-contradiction here says not contradiction, right? Sorry, this bracket. And when we say not something, we mean something is false.
Mm-hmm.
So that's why it's called law of non-contradiction.
So then if inside the bracket's always going to be false, and when you negate it, it's going to become true.
No. So what does this is? So this is false, right? And when you do that, it's going to be true. And like when you apply De Morgan's here, what are you going to get? You're going to get Q or not Q, which is a tautology. And tautologies are always true.
Yeah.
That's why it's called law of non-contradiction. It's called non-contradiction because it's saying that contradictions are not true or contradictions are false.
Okay.
Yeah, it's just like a conventional thing. Yeah. So this is abbreviated as LNC. Okay. There are other rules, other laws called law of non-identity, law of identity, law of excluded middle, and then law of non-contradiction. But yeah, like law of non-contradiction is just like the granddaddy of all logical laws. And then okay, so now you know that this is false, right? You know the truth value of the consequent. The truth value of the consequent is false. you know that the implication is true because you started with this, you ended with this, so it means the implication is true. So what has to be the truth value of the antecedent for the implication to be true while the consequent is true?
So we said it needs to be false.
Yeah, but why?
Because if it's true, then it will be false because that's the one condition where an
Exactly.
implication.
Exactly. So if I'll show it to you in another way, okay? So this is true, right? So
Yeah,
this is true because you started with this, ended with this, so it means the implication is true, right? And what you're essentially saying is not Q and not Q. Okay? This is just a like a statement of non-contradictions. Law of non-contradiction says contradictions are false. So not Q and not Q, and you just do modus tollens on that, and you get not P, which is the same as P, right?
yeah.
You follow that? So do you get this part? This part?
Yeah, so we just did modus tollens on it.
Yeah, we just did modus tollens on it, and
Oh, then
yeah,
if it's mod. Oh, yeah. Okay, yeah. It's modus tollens. Yeah.
yeah, it's modus tollens, and this is just the statement of law of non-contradiction. This is how it's formally stated. It's not the case that X is true and X is not true. Okay?
So then P is true.
Then P is true. So you started with your false assumption. You started with an assumption. You arrived at a contradiction, and then you reason backwards. You modus tollens backwards to say that your initial assumption was false. Therefore, whatever you wanted to prove is true.
Yeah, I think I'm following.
Yeah.
I'm still not quite sure why it's called the law of non-contradiction, but if I think about it, maybe
Yeah.
it'll come to me.
Yeah.
But it's correct when they say when you put the negative, with the negation in front of the contradiction becomes true or not.
What?
So so when so the contradiction is normally false all the time, and then when you put a negation outside the brackets,
Yeah.
the whole contradiction is becoming true.
No, contradiction is not becoming true. When you put the negation outside, you are basically turning that proposition into a tautology. You are, you know, the contradiction is already false, right?
Yeah.
And you are negating it, which means you are converting the contradiction into a tautology, which is always true.
Okay, so it's not the contradiction becoming true, it's just you're converting it
Yeah.
into a tautology.
Yeah.
Okay, yeah, I think I roughly follow.
Yeah, I mean, even if you say the contradiction is becoming true, it's basically becoming a tautology. So it's in one sense it is true, but if you say contradiction is becoming true, that like it's a bit of like a misleading way to say it, state it. Like people might construe that as you being a dialetheist, like somebody who thinks that there exist some true contradictions.
Okay, so what people might assume I'm being what?
A
What was the word?
dialetheist. Yeah. One sec. I'll write that down. One sec. Come on.
Is it similar to a sophist?
No, not really. Um, This is actually like a serious philosophical position. So dialethists are people who reject the non law of non contradiction. And there are like actual like serious logicians out there who take this view. um, I am not convinced of it. I am not persuaded that it is the case, because like I am not really sure what it means for a contradiction to be true, you know. It's like a conceptual thing. So I just don't know what it means for a contradiction to be true. um, and like I don't find dialetheism as a position to be coherent, um, like intelligible or whatever, you know. But yeah, like this is an actual position out there. I just wanted to say that, that there are diletheists and they are like there are serious logicians. It's different from sophists in the sense that sophists are like, you know, dishonest motivated reasoners or whatever. This is not really that kind of like a thing.
Okay. But overall, the law of non-contradiction is saying that a contradiction is always false.
Yeah,
That's it.
all contradictions are false. You can also
Okay.
say it's not the case that there exists a true contradiction.
Okay.
Yeah.
But if I said the law of contradiction, would people understand what I'm saying, or do I have to put the
People
non?
might understand what you're saying, yeah, but like the convention is to say law of non-contradiction.
Okay, I'm gonna need to have a think because it's for me it's a bit confusing what the non is doing there. Yeah,
Yeah, I guess yeah. If you maybe ponder about it, you might, yeah.
because
I'll
the
see if
non
I can find like a more convincing.
because
Uh,
the non is representing the tautology bit of it.
uh, Wait, what do you mean?
So because when you add the non,
Mm-hmm.
you're converting it to a tautology.
Yeah.
So, so for me, it's a bit confusing because then the law of non-contradiction, then once you're converting it to a tautology, then it'll be true, the all the values as we saw below there.
Wait. I don't get you. What do you mean?
So the when you add a negation to the contradiction,
Mm-hmm.
it becomes a
A
tautology.
tautology, yes.
So then, so the law of non-contradiction, yeah, then it's sort of the non, when you add the non to the contradiction, then it's becoming a tautology.
Yeah.
So that is that what the non part of the law means? That you're converting it to a tautology or not?
So the non means no, right? Like non just means no or not or something like that. And we are just saying not contradictions. Like contradictions are not true. So like when I say not P, right? When I say not P, what do I mean? I mean P is false.
Okay, so here you're saying the law of non-contradiction just means that contradictions are false.
Exactly.
Okay, I think I got that then.
Yeah. That's all. That's all it means.
Yeah, that's cleared up.
Yeah. Yeah. Um so I
So we've
guess
done a lot.
that should be good enough for today.
Yeah, I
uh,
can try. People can try, whoever's listening, they
yeah,
can go to the book and try and prove it using reductio
ad
ad
absurdum.
absurdum.
Yeah. So at this
Right
point,
then.
we are like at this point, I think we have covered all the rules. Well, not really. We still have the biconditional yeah, replacement rules, but this is more like this is all like this should this should get you wherever you want. Um the biconditional rules, they're just like additional rules, but all of these rules should get you wherever you want to go. And like, of course, now you know the reductive ad absurdum. Um, so yeah, that should get you where you want to go.
Up to predicate logic.
Oh no, predicate logic has more rules.
But,
There are
but,
more
but this but this will get me up to predicate
up to
logic.
predicate logic. Yes, it'll get you
All right,
to the
that
footsteps of predicate logic. Yes,
all right, that's not too bad.
the doorstep, not the footsteps. The doorsteps of predicate logic. That's right.
Yeah, it's all about practicing all of this stuff.
Yep. Yeah, we've look at that. Look at what we've covered so far. Damn, look at all of that. It's quite a bit, right?
Yeah, definitely high level stuff.
Yeah. But remember where you were over here, and remember where, and realize where you are right now. Like it's just night and day, right? Like hardly like 10 hours into this.
At least I know what a truth table is now.
Yeah.
Yeah, because that stuff seems daunting if you're looking at it from outside.
Yep. But you know, when you get intimate with these things, they're not daunting anymore. Like once you know what it is, it's not scary anymore.